Hello, calculus students, and welcome to what we call Cycle 6 Accumulation and Average Value. So with this video, we're assuming that you know the concept of integration. We're assuming you know that integration is a summing principle and that you have done left-hand, right-hand Riemann sums, maybe trapezoids, midpoints, and it's all about accumulation, adding up stuff. Here are a couple of problems that I think might be best on video so that we may not do them in class, but that you can access them, slow them down, stop as many times as you want. Traffic flow is defined as the rate at which cars pass through an intersection, measured in cars per minute. The traffic flow at a particular intersection is modeled by big F of t equals 82 plus 4 sine t equals 2, t over 2 for 30. This is 30 minutes, where f of t is measured in cars per minute and t is measured in minutes. There are three pieces here for this problem. Part A, is traffic flow increasing or decreasing at t equals 7? Whoa, so that means an increasing or decreasing answer, that's really a first semester calculus problem, just to see, hey, is the first derivative positive, negative, or zero? So in this case, because the function that we have is actually a rate already, it's like we want to find out the rate of that rate, or like how that is changing. So we seek, in this case, big F prime of 7. So we want to see if the flow is increasing or decreasing at t equals 7. So I'll write the function here. F of t is 82 plus 4 sine t over 2. So big F prime of t is going to be, let's see, this is the sum rule, and then double check that the derivative of 82 is 0, and then the derivative of 4 sine t over 2, that's going to be a that derivative of that 4 will be a constant. Man, it's been a while since I've taken derivative using chain rule. And the derivative of sine is cosine t over 2. And then we also have, so it's cosine t over 2 times 1/2. And we'll clean that up a little bit. That becomes, let's see, 2 cosine t over 2. After that, we just plug in a 7. So big F prime of 7 is going to be 2 cosine 7/2. And I probably put that into the calculator. That ends up being around negative 0.187. So traffic flow is decreasing because F prime of 7 is less than 0. I think I have notes here that I've just made a quick view of that one for minutes of that function and cars per minute. And we're going from like 0 to 30 minutes, and I believe it was, oh yeah, because 82 is like that's the base level, and then it's a sine function. It kind of behaved like this. And so it looks like at 7, I'm estimating here, that was 7, the derivative was negative. That means the slope of the tangent line, or the rate of change of this rate, is decreasing. So traffic flow is decreasing. Okay, I made that graph because in part B I knew we want to find the average value of the traffic flow over the time interval 10 to 15. I'm going to clean this part up a bit here to show you, average value. There we go. From 10 to 15, let's put 10 to 15 in there, is that we've got some value at 10, we've got some value at 15, and if we take the integral of that, because this is minutes times cars per minute, that area under the curve there is just cars. And that's not an average value. What we need to do then is divide by the span of time that we've used, which is 10 to 15. So in math speak, that is the, we want big F, and I'll put AVG for average, is going to be, first we take the integral from 10 to 15 of f prime of t dt, and we take it over 1 minus 15 over 10, which is going to be over 5. That ends up being, by the fundamental theorem of calculus, the integral of this derivative is 1 over 5 times the integral from 10 to 15 of this function, 82. Wait a second, I don't know if I should have a prime there. I think this is just f, big F of t. I think that's just 82 plus 4 sine t over 2 dt. Yeah, we want the value of that function, which is already a rate. And so now I would probably put that into a calculator. You could, if you knew the u substitution, probably find it for this 4 sine t over 2. But I think right now we can put that into the calculator. I'll show you what that is using u sub, and you can confirm the derivative once, the antiderivative once you have it, but you may not know how to find this yet. It is 8 cosine t over 2 from 10 to 15. All right, I'll keep doing it the long way here. That means it's 1/5 times 82 times 15 minus 8 cosine 15 over 2 minus 1/5 times 82 times 10 plus why is that a plus? Maybe that should be a minus. Plus 8 cosine 15 over 2. I need to double check my notes. I have a plus there. Can't remember. Oh, maybe I've distributed this. I believe that is still a minus. Just in my notes I haven't. And I believe that ends up being 81.9 cars per minute. The average value of the traffic flow. So that means the average value of all that space, there is some number between here and here that is an average value. And it looks like it's very close to the, it's a little bit under 82, like 81.9. That means that is of all the areas under the curve, the average value for y is 81.9. Okay, last one there, the average rate of change of the traffic flow over the interval from 10 to 15. Okay, this one, average rate of change, that's a slope of the secant line. We don't take the derivative, we don't have an integral. The slope of the secant line is the average rate of change for us in calculus. So, man, let's go back to from 10 to 15. That means then this is roughly here. At 10, there's the rate of change, and then at 15 there's a rate of change. We are looking for that slope, which is the slope of the secant line between f of 15 and f of 10. Rise over run. So we've got it in words down here. Now in the values, that's big F of 15 minus big F of 10 over 15 minus 10. And you've got to find values for those. F of 15, I put them into the calculator. I get 85.752 minus 78.164 over 5. That is roughly 1.518 cars per minute. It makes sense. That slope is positive, and so it looks like the average rate of change, or the average slope of the tangent line from 10 to 15 is a 1.518 cars per minute. All right, there's an average. This is more of an average value problem.